My name is Zephyr Li, and this is what I'm working on understanding the characterization mechanism of advanced magnesium alloys. I'm working with Professor Barley and Long under the Department of Mechanical Engineering and Materials. So to begin with, imagine you live in downtown SB and you get to work here every day, and you have two vehicles to choose from. Now you're a kind of poor student and you want to save money, so which one would you? Which one about the Honda?
The white one.
Yeah. Well, not only because the Honda motorcycle will be cheaper, it's also because nowadays where gas price can get kind of crazy, it will be very nice to have vehicles that can save gas. And of the two vehicles, one of the major factors that determines how much gas is used is the weight of the vehicle. The Honda is much lighter than the truck, so that's why we'll generally save more gas. But what if we can use the materials that is much lighter than the current material used, while it can maintain the structural properties of stronger materials? Then we can create lighter vehicles that's more fuel efficient and that can travel more distance. And this is actually a big issue, big problems that structural materials have been trying to solve, in which they always try to find a lighter and stronger material. And this is where magnesium comes in. Magnesium is a lightweight, abundant, and very lightweight material. It is the number 7th most abundant element on Earth, and out of all the structural metals currently used, it is the lightest out of them all. With its great properties, sometimes we can see it being used in camera frames or other purposes in which lightweight is extremely important. However, we still don't really see magnesium at all in industry, mainly because of its major con of, in its pure form, it is very susceptible to corrosion and fracture. In fact, in the 1960s, magnesium was originally used to create alloy wheels, but then over time, people found out that magnesium wheels does not have a long lifetime at all. It will crack very easily without much use, and now this is slowly replaced by aluminum. But if we can find a way to enhance magnesium's properties while maintaining its greatest pro of being lightweight, then we can create very efficient machines that is very fuel efficient and extremely effective. And there actually is a process in order to achieve this called alloying. Alloying is a process in which we have a base material and we fuse it with small amounts of other materials in order to create, and the particles within the material will somehow align together in a microscopic scale in order to create something much stronger. One example of this is steel, in which iron is a material that's rather soft in its pure form, but if you combine it with a little bit of carbon particle, you'll create steel, which is a very strong material that is one of the most commonly used in industry nowadays. And what about magnesium? Well, there is actually a formula that's been recently developed that can create a pretty effective magnesium alloy. You add like 3, 4, 5% of aluminum, 1% of zinc. You can get a pretty good result of a strong magnesium alloy. But the problem is we don't really understand it. Like we don't really understand why does it work so well. And by altering the percentage, we can get different results, which we also don't understand why does that happen. So the general research questions I will try to answer this summer is, what microscopic mechanisms that will allow this new advanced magnesium alloy to be stronger and more ductile? And to do so, I will start with, my research will start with material characterization, which refers to the process in which we prepare a material to examine it in a laboratory setting. Because like, obviously we can't just bring this to a lab. It's going to be kind of difficult to analyze. So basically, my mentor will prepare a pure sheet. Like usually it's just a block of material, and then I'll first cut it and depending on how the material is made, different surface will reveal different property of the material. So I will cut it at the surface I will like to analyze, and then mold the different pieces together and polish the prepared specimen in order to remove any of the impurity on the surface. After all this process, we'll have a prepared specimen like this in which we can see the different surfaces and After this specimen is created, I will soak it in an acid for a little bit to reveal the microscopic structures on the surface, which can be later analyzed using SEM. SEM is called scanning electron microscope. It's a microscope that shoots out a beam of electron onto the surface of whatever object that's in it, and then the electron will bounce back and the machine will read out, will display the readings in order to create a very detailed image of the surface, which is shown right here. Now this is called texture in material science. Texture generally just refers to how the structure of the material looks like on the surface. And there's two very main points from texture called grain. They're called grain. The main thing from texture is called grain, which is every little piece, that's outlined by the boundary. That's a two important factor of the grain. One of them is grain size, the other is grain orientation. Through SEM, I can measure the grain size. Now, this is an example image of from the scanning electron microscope, and the yellow part outline the particular grain. And what I'm going to do is take a lot of images like this, and then just measure the length and width of every single grain that's kind of visible, and then take the average of the length of grain in order to measure the grain size. And this is an example of the data distributions that I got from one of the magnesium alloys that I tested. And generally speaking, for grain size, the general statement is the smaller the grain size, the stronger the material is. And from my experience in the lab over the summer, most of the material, the mean distribution will be at the average I've gotten for most of the materials I worked on is between 2 microns to 4 microns. And this frequency distribution pretty much shows that how different grain size is distributed in a particular alloy. And this information will be very useful later on for us to compare with other alloys. And that part SEM in the specimen is for the more microscopic property of the material, but we can also test the structural property for tensile tests. Tensile tests, you utilize a tensile test machine which will provide a load at the top and bottom, and there will be a specimen in the middle right here, and there will be a load that's applied to the sides, either in the form of tension or compression. And there will be a laser that's pointed at the material in order to measure the changing length. Because once you stretch something or draw something, the length, even though it might not be visible in the human eye, it will actually change. And through a laser, we can actually measure that. And after this process, we can form a data. That is one of the most simple, most basic, and most effective way to define the structural property of the material called the stress-strain curve. Stress is the force over the area that pretty much represents the load that is applied to the material, while strain means the elongation or the change of length divided by the original length. That represents how much the material has been elongated or shortened. And this part of the graph is the elastic region. It pretty much means that once you load the material, as long as it's within the elastic region, if you release the load, it will bounce back to its original state like spring. But if you move to point 2, in which it's above the elastic region, then when it bounces back, it will fall back to this state. So there will be some sort of permanent deformation going into the material. And generally speaking, we will want our material to have as high of a elastic limit as possible, so that I will want the stress to be as high as possible. And then we will also want this range to be longer. As the longer that part is, it means that the more the material can bend before it breaks. And at this point, it's where the material breaks. So this is kind of a basic image of what a stress strain curve will look like. And this is a more advanced image of what a particular magnesium alloy called the WD44 is. We're really interested in this alloy because it has some amazing properties. So first of all, let me explain what the abbreviation on the graph is. TD stands for transverse direction and RD stands for rolling direction. Like when we prepare material, it's based on the way when we prepare material, usually it's like a lot of stuff that's extruded through a thin nozzle. And as a result, in the rolling direction, the grain will usually be smaller, whereas if you look at the transverse direction, the grain will be larger. And since the material I'm working on usually creating a cylindrical shape, so there isn't going to be a difference between the long and short. But yeah, as you can see, the red and the green graph highlighted the different directions of this W43, while the black plots highlighted the information that's on like previous magnesium alloys that's created several years ago called the AZ31. And we can see that just in a few years of time, there's a major improvement in which this new alloy has much of a higher range compared to the AZ31, means that it will take a lot more force to deform it. And on top of that, for magnesium in particular, it's a material that's been known for, like based on the way you prepare it or based on the way you load it, you'll get really different results. However, when you look at the red and green over here, these plots align almost identical to each other. This is a really, really good property for magnesium because of how in the past magnesium has been infamous for just having crazy orientation based on the way it's created. Okay, so as of now, I've collected a lot of data about the grain size, the grain rotation, or the stress and strain. But a lot of these are based on experimental results, and it's probably impossible to test everything since there are so many variables that we can easily change and we'll need to perform another test, which may take hours. So what we can do is to create a model, and in material science, there's a model called the viscoplastic self-consistent code. And what this does is it can take the inputs such as grain size, grain orientation, and temperature, the microscopic stuff that I mentioned earlier, and you put them in the VPSC code. And as a result, we can get the stress strain data. And most importantly, we can get the deformation mechanisms, which is about how within a material, how the particles within it, like say a material is in a break, we can know within the material where does it start to break first. And this information is really crucial for analysis, but like for this code, we need to calibrate it with data. And currently, what I'm trying to do is to collect enough data so that I can calibrate the code so it can fit the particular need to analyze magnesium alloys. So just to sum up, the first step that I'm doing is to understand the current alloys through different tests and collecting data. And later on, with all the data, I can try to use this information to calibrate the VPSC code in order to predict the general behavior of magnesium alloys. And eventually, with enough people and enough time has been spent on this project, we can find out a effective way to utilize magnesium or even create a stronger magnesium alloys than before. In order to utilize magnesium in industry to create more efficient structures or vehicles or machines, and we might be able to create vehicles that is light and saves gas. So thank you all for your patience, and additionally, I would like to acknowledge Professor Irene Barling for introducing me to this field, and my mentor Alon, who has been really patient in explaining all this stuff. Like he pretty much taught me every procedure that I described earlier. So first, thanks to him. And then I appreciate the Gorman Scholar Program, CNSI, and CSF for providing me this wonderful opportunity to getting a laboratory setting. Thank you all.